cosmologist at Argonne National Lab. So a little bit about myself. So I particularly work in computational cosmology. My background is in sort of large-scale structure theory, and I've been particularly focused sort of since postdoc days and present day to, on the galaxy halo connection, and then especially recently. Well, I guess I've always sort of had an interest in scientific computing, but recently I've been especially interested in differentiable programming, which I'll talk a bit about later in the lectures. I grew up in New Orleans, and I'm a big fan of all varieties of street parades. I'm a special lover of a funky tuba in a street parade. I love many sort of Chicago-born foods. I'm very partial to the thin tavern-style crust Chicago pizza, but Chicago has many sandwiches that were born within the city confines. I especially love what's shown here is a gym shoe, but a close second is the Heberito. I'd be happy to speak at some length on Chicago-born sandwiches, if anyone's interested. I love heist narratives, detective stories, detective fiction, and in general, I really enjoy sort of figuring out the way that narratives work. I think maybe one of the things I like about heists is just they have sort of many well-defined rules that are sort of meant to be broken. And the 10-minute game is a kind of long-standing conjecture and kind of fun game that I play about sort of, the conjecture is really that really the entirety of a film is contained in its first 10 minutes, sometimes less, sometimes a little more, but essentially the central conflict and even how it will be resolved, how a character's development, what their central conflict will be, and whether they will learn anything or nothing at all. Anyway, let's see. Oh, and then I really enjoy hiking and kayaking. So this last photo is one of me kayaking in the Chicago River, which is a place to put in a few blocks from my house. So this is one of my favorite things to do in the summer months in Chicago. So let's see. That's a bit about me, a bit about what I'd like to sort of share with y'all in these next few lectures. So this first lecture, I'd really just like to give you some sort of background cosmology motivation for the galaxy halo connection, especially cosmology in the nonlinear regime and the role of simulations. And I'll jump straight to takeaways. So the key takeaway sort of from today's lecture is just that we do not directly measure what we can directly predict with our theoretical tools. And I'd say if there's one overarching message, even for people who are not either going into the galaxy halo connection or not as interested in this particular topic, I'd say that's the key takeaway for all 4 of these lectures. So the second lecture today will be about abundance matching. This is sort of the simplest of all galaxy halo connection models. And again, so the key takeaway here will really just be that even though galaxy formation physics is enormously complex, the sort of emergent scaling relations that arise from galaxy formation are very strikingly simple. And so then tomorrow, I'll change gears a bit. I'll talk a bit about some sort of new insights into galaxy formation physics and the galaxy halo connection from the stellar to halo mass relation, but really that's sort of a toy model that I'd like to use to motivate differentiable programming and differentiable techniques that are made possible by AI libraries that have become very common. And so for that lecture, I'll have a Google Colab notebook that I'll share with you so you can have some sort of hands-on experience with these sort of new techniques. And then finally, in the last lecture, I'll talk about the halo occupation modeling, the HOD, CLF, and ways that we can do cosmological inference with simulations. And there's some nice, I think, overlap, sort of intersection with machine learning AI techniques, and especially in cosmological inference with the HOD. Okay, so let's see. Right, so we've already heard a lot about the cosmic microwave background. Eve had some really nice lectures yesterday and today, and so I really just want to give a quick recap of the sort of core facts about the CMB that sort of motivate large-scale structure cosmology, particularly in the nonlinear regime. So all of those are actually sort of, in a nutshell, contained on this slide. So the basic facts about the CMB, they've heard a lot about already. The CMB gives you a very detailed picture of the universe at sort of early times, around redshift 1100 or so. The spoilers from that detailed picture are really just that the universe is a near perfect black body. Perturbations about that black body are adiabatic perturbations at 1 part in 10 to the 5. Adiabatic just meaning that baryon overdensities sit atop dark matter overdensities. That's a key important feature for galaxy formation physics. And that really those over and under densities grow and evolve to become the large-scale structure in galaxies that we observe today with our telescopes. So in a nutshell, this is the background of the CMB for large-scale structure cosmology, and in a slightly deeper dive. So the basic evidence for why we sort of know the early universe was a near perfect black body was just because we have direct measurements of the temperature spectrum. This has been known since the early 90s from the Virus satellite. And really, I think the takeaway here is really just a mental map of sort of what the CMB is telling us about the early universe. You can just think of it like a homogeneous bath of protons and electrons and photons, where acoustic oscillations about this sort of homogeneous background are sort of propagating all the way up until the time of last scattering. Let's see. I thought I really liked Eve's sliders showing how you can sort of toggle different effects in the cosmological model and see directly with your eyes how that modifies the temperature anisotropies in the CMB. And to me, that just makes it just very compelling how such a simple model of Lambda-CDM cosmology is just incredibly richly predictive. So this is just the full structure of the temperature anisotropies are just described by sort of essentially the 6 vanilla Lambda-CDM parameters. I think to me is just a striking success of sort of contemporary cosmology. And so let's see. This is the kind of cartoon picture that I keep in my head when I think about acoustic oscillations in the early universe in this tightly coupled sort of photon plasma. And my obligatory pie chart summarizing the basic takeaway of standard model of cosmology, just that here again we have a very, very simple model making highly complex predictions that are in terrific agreement with observational data. But despite that success, well, let's see. Yeah. Despite that success, so even though Lambda-CDM is highly predictive, it's also very, very unsatisfying. I thought Tessa's lectures did a really good job of shining a light on this. So fine-tuning problems with a cosmological constant, that sort of completely unexplained reason why omega matter and omega lambda are of order the same density. So this is definitely unexpected. If you interpret the cosmological constant as a vacuum energy density and you interpret the matter over density, the abundance of dark matter is being due to some sort of freeze out, a thermal relic freeze out, then there's really no physical connection between these two mechanisms giving rise to these contributions to the energy budget, and yet they're of order the same abundance today. So there's many aspects of this theory that even though they're very predictive and successful, they're very unsatisfying. And so for me, this sort of motivates going beyond, at least going beyond standard temperature, power spectra, CMB measurements, just trying to get a bit better picture for what the underlying physics that gives rise to these observations. So in going beyond the CMB, so particularly with large-scale galaxy surveys, this is the area that I work in especially. The sort of cleanest probe of all when it comes to a galaxy survey certainly is baryon acoustic oscillations. This is a characteristic peak in the 2-point clustering of galaxies seen around 105 megaparsecs. Actually, the first direct observations for the first direct evidence for dark energy came from measurements of type 1a supernovae. Both of these are sort of pure geometry probes, meaning that when you make predictions for what these signatures would be, essentially all you need is predictions of the expansion history itself, so that both BAO and supernovae really just give you information about the geometry history of the universe and not how structure grows over time. This is a slight lie in that large-scale structure nonlinearities do impact VAO measurements in a very small amount. My bet is that Will touch on this at least a bit, at least mention this in his upcoming lectures. But the main picture here for now is really just that sort of our best evidence for dark energy really just comes from either early universe measurements or pure geometry probes, but not probes from sort of structure growth, especially historically. And so this is especially true for the recent measurements of, that I think have been mentioned many times in these lectures already, of evolving dark energy. So right now we have geometric evidence for evolving dark energy, tentative as it may be, but not structure growth measurements. And so this is a major growth area, I think. And coming sort of near-term cosmology is constraining our cosmological model with measurements of structure growth. And so this is the area that I'll be focusing on. So a little bit more about BAO. So because this is a measurement that we derive from measurements of large-scale structure measurements of galaxy surveys. Even though it's a measurement of galaxies, again, as I said, it's a pure geometry probe. And so what is this probe? So galaxy clustering is just defined as in terms of a 2-point correlation function. So what is that in a brief amount of detail? So the 2-point correlation function just observationally, operationally is defined as the pair counts in excess of random as a function of spatial scale. So if you go out with a pair counter and you measure pairs of galaxies separated by a given distance, and then you measure the pair counts of a random distribution of points separated by that same spatial scale, that ratio is the 2-point correlation function. This is how it's observationally measured. And this characteristic peak that you see in the 2-point correlation function of BAO, here it's just directly visible by eye. This is sort of in broad strokes exactly how this is observationally measured. So going back to this mental map of acoustic oscillations in the early universe, so why do we have this characteristic peak, this BAO signature? So it corresponds directly to essentially the distance that the largest distance that a sound wave can travel before the time of last scattering. So you have some characteristic peak, and then you have this ripple. Then the farthest this ripple can travel naturally gives you a overdensity in the galaxy distribution that traces the overdensity in the early universe. And so you get a characteristic overdensity at this exact distance from essentially the distance of the sound horizon at the time of last scattering. And so it's in this sense in which the BAO peak is a pure geometry probe. So you do not need to know how much structure has grown over time in order to be able to predict it, but you do need to know what that characteristic distance is. So that is qualitatively different from other probes of cosmology by galaxy surveys, for example, galaxy clustering, galaxy-galaxy lensing, which directly probe how much structure grows over time. So how these overdensities increase their height over time. And here's the sort of basic picture for the way large-scale structure proceeds. So you have nearly homogeneous initial conditions in the early universe, and then linear perturbation theory gives you essentially a no wiggle room prediction for the abundance or for the correlation function for the power spectrum on very large scales. So there's no sort of free parameters that you can toggle in making predictions for the power spectra in the linear regime. This is a direct prediction of general relativity. However, on smaller scales, when overdensities continue to grow, perturbation theory breaks down irreparably. So you can go beyond linear theory, second order perturbation theory and beyond to be able to extend your predictions to slightly smaller scales. But eventually perturbation theory breaks down irreparably and you just have to rely on cosmological simulations to be able to make your predictions. So why would you want to do that? So cosmological simulations are messy, nonlinear structure growth is complicated. And so this figure sort of gives my nutshell kind of theory level motivation for cosmology essentially in the nonlinear regime. So what you're looking at in this figure is on the vertical axis is the constraining power, the statistical constraints on W0. So just the value of the equation of state of dark energy today, as a function on the horizontal axis of R min. So R min is the smallest spatial scale that you use in your analysis of, in this case, galaxy clustering is what's shown. So again, imagine going out to your observational survey and measuring your pair counts as a function of spatial scale. As you go to smaller and smaller scales, your measurements are more and more impacted by nonlinearities. And in this figure, you can see as you go towards smaller and smaller scales, the curve goes down and down and down. So the constraining power increases and increases and increases. So you get tighter and tighter constraints the farther into the nonlinear regime that you can go. So The reason why this is especially challenging going after cosmology in this nonlinear regime is just because there's tons and tons of systematic uncertainty of a variety of kinds that impact your ability to be able to make predictions in this regime. So on very large scales, again, the purely perturbative regime, you're not impacted by nonlinear structural growth by definition. And the very first sort of complications arise from just sort of garden variety nonlinearities in the sort of very early breakdown of perturbation theory. So I'm just generically referring to this as gravitational nonlinearities. And BAO is just on the hairy edge of being not quite negligibly impacted by this. As you go towards smaller scales further, so past the quasi-linear regime, on scales of tens of megaparsecs, now you really need to rely on techniques from the galaxy halo connection in order to be able to make predictions for galaxy clustering, coupled with cosmological simulations. So these predictions for the galaxy halo connection cannot be made in a vacuum. They're made in a tightly coupled way to cosmological simulations. And eventually, as you go towards still smaller scales, you're impacted by baryonic effects. The fact that, for example, if you have your predictions for the nonlinear regime based on a gravity-only n-body simulation, well, you're missing key physics that does redistribute mass on scales of 1 to a few megaparsecs. So for example, even on scales of 1 to 2 megaparsecs, if you have a particularly active AGN, a black hole in the center of your dark matter halo, the mass distribution can be impacted by baryonic physics that's just not captured in your simulation. So you need to rely not just more on the galaxy halo connection, but also on models for baryonification or for baryonic modifications to the mass distribution. So this figure sort of gives a rough quantification for the major improvements that you can get in the constraining power on dark energy. And for me, this is already a very strong motivation to try and see how we can do with improving the quality of the models that we apply to be able to make our predictions. But beyond just sort of vanilla dark energy constraints, the nonlinear regime also just opens up qualitatively new probes of cosmology, particularly modified gravity. So things that are entirely inaccessible to geometry-only probes all of a sudden become available if you can have sort of trustworthy, reliable, robust predictions into the nonlinear regime. And really, I would just say, so the statistical constraining power, I think, is really very strong. So many different groups, I think, now are pursuing different cosmological probes, which get significant benefits from going into the nonlinear regime. And really, the statistical constraining power is in some sense misleading because this is really a systematics-dominated regime. So the era of precision cosmology is really better named the era of systematics-limited cosmology. And this is especially true for structure growth probes in the nonlinear regime. So we really just have to rely on simulations in an essential way in order to be able to get our information about cosmology sort of in this regime. Okay. So the key technique to be able to make robust predictions in the nonlinear regime is cosmological simulations. I'll talk a little bit about hydro simulations a bit later on in these lectures. For the most part, I'll be focusing on gravity-only simulations. So that in a quick nutshell, the way that these sort of simulations proceed, so you start with CMB motivated early sort of initial conditions. You discretize the density field at very early times, and you set it up such that your initial power spectrum sort of exactly matches constraints from the cosmic microwave background. And then you essentially use a force solver on this discretized density field, operating on tiny time step by tiny time step by tiny time step on millions, billions, or trillions of tiny particle mass tracers to solve for how the density field evolves in the nonlinear regime. So we've already actually heard some nice lectures by Simeon on cosmological simulations, so I'm not going to go into any detail here, although I particularly like this recent modern review of cosmological simulations by Rollo Angulo and Al-Rahan. So I think my PDF links come through. I also will share my Google Slides. I have many, many links to sort of additional information that are sort of embedded throughout these lectures. So great. Okay, so the next sort of several slides, I'm going to talk about sort of the key facts about how LCDM structure grows over time and sort of what are its fundamental building blocks, particularly the dark matter halo. So you should think of a dark matter halo really as just a gravitationally self-bound collection of dark matter. The simplest models of dark matter halos are sort of typical spherical cow type models in which you have some spherical overdensity that gets denser and denser as you go towards the center. This is not an essential feature of a dark matter halo, but this is really, I think, the mental model that I have of sort of what is a dark matter halo. And so this is a sort of isolated dark matter halo where it's very apparent where you would sort of draw the circle, and that's the circle around this overdensity, and that's intentionally chosen, but in reality, a cosmological simulation is a big mess of over and underdense peaks. And so we have to rely on bespoke algorithms like halo finders to first find peaks in the density field, and then around each peak, you sort of, depends on your halo definition, but the classical spherical overdensity definition, you go to you go to a particular peak, you grow a sphere around of successively larger and larger radii until the interior density is equal to some particular threshold of the mean density of the universe. And once you've reached that threshold, you say, aha, I have found the dark matter halo, and I will discard any other peaks that I might have previously found in my peak finder that happen to lie within that radius. I'll go to the next largest peak. I'll grow another sphere. I'll grow it again to the same until the same critical threshold of density is reached. I'll have found another dark matter halo, and you'll proceed on and on and on. And in modern cosmological simulations, millions to billions of dark matter halos are identified and found in this way. And so, so far we can think of our cosmological simulations as essentially a prediction engine for the abundance and distribution of dark matter halos. So from a given cosmological model, a cosmological simulation gives you, again, essentially no free parameter prediction for the abundance of dark matter halos. So how are the statistical properties and internal properties of these dark matter halos quantified? So the sort of very first fundamental summary statistic of dark matter halos is just the halo mass function, just the abundance of dark matter halos as a function of their mass. And so what you're looking at in this figure as a function of halo mass is just number density in a megaparsec cube. Different redshifts are shown with different curves. Then here I've also used different cosmological, it looks like a varied omega matter, just to show you roughly how the abundance of dark matter halos is impacted by cosmological parameters. So qualitatively, we can make very good predictions for the halo mass function. With elementary theoretical tools, extended pressure formalism gives an excellent sort of 10% level prediction for the abundance of dark matter halos. And a general sort of theme you'll sort of hear me refrain throughout these lectures is just that we do have sort of fundamental theoretical tools to be able to make predictions for the key quantities in large-scale structure at roughly the 10 or 20% level of accuracy. And really, if you want to do precision cosmology, you just have to rely on cosmological simulations to give you a finer-grained, more accurate prediction. Let's see. Oh, maybe one thing that you can see just from this figure also is just that, so at a given mass, very high mass halos at higher redshift are rare, and it takes time for structure to grow over time in order to be able to form massive halos. And so at a fixed mass, you see the abundance of dark matter halos go down and down and down with increasing redshift for this reason. Yeah. Okay, sure, yeah. Another key sort of summary statistic of really the abundance and distribution of dark matter halos is the halo bias function. So bias refers to the excess clustering of a given dark matter halo relative to the matter density field. So if you were to go out again with your pair counter, measure the matter correlation function on a given scale, and then do the same thing with your dark matter halo correlation function, take the ratio, take its square root, and this is the bias as a function of halo mass. So bias generally increases as you go towards, or generically increases as you go towards higher mass. And the kind of extended press sector way of understanding this is really just that the rarer the object, the more highly biased you should be, and more massive halos are more rare. And so you can see this general trend as a function of both mass and redshift. And again, here I've just shown the general effect of varying cosmology on the bias function. And let me see. Yeah, so maybe here, let me also add a refrain that I've said this once already, but you can see because the halo bias function varies with cosmological parameters in a way that we can directly predict, what we would really love to be able to do, say with the halo mass function, is just go out and count observed dark matter halos. Drop a megaparsec box, count the number of halos as a function of mass that falls in that box, and then directly infer cosmological parameters. Constrain them even better by directly measuring the two-point clustering of dark matter halos. And those are things that we can predict with a simulation, but we cannot directly observe. So it would be terrific if we could, for example, if galaxy cluster cosmology could actually directly observe massive dark matter halos, but instead you have to rely on a cluster finder to be able to have a mass observable proxy for dark matter halos. And so this is true throughout all of large-scale structure predictions. So this figure gives you kind of the root level information content of halo clustering, but we need to rely on a model for the galaxy halo connection, which gives us something we can actually directly observe that we can predict. So much for the abundance and spatial distribution of dark matter halos. So what about their internal structure? So what you're looking at here is a simple figure of the famous NFW profile, the Navarro-Franken-White profile. At the time that this was sort of discovered, it was not obvious at all that there was a universal structure, internal structure to dark matter halos, but it turns out to be roughly true. That there's a sort of broken power law density profile that is seen throughout all of Lambda-CDM, and really even sort of non-Lambda-CDM models exhibit this general behavior of a broken power law density profile as a function of radius. And so that you really just have a kind of one parameter family of descriptions of density profiles by this concentration. So higher concentration halos tend to have more of their mass concentrated towards the center. So the internal structure of dark matter halos carries a memory of the formation history of the halos. So there's a lot of information that's contained in its internal structure that's directly connected to the large scale distribution of those halos. So what you're looking at in this figure is how halo concentration varies with halo mass. And generally speaking, high mass halos tend to have very low concentration, and lower mass halos tend to be much more highly concentrated. And this is not shown in this figure, but this is also true of the correlation between halo concentration and halo age. So older halos tend to have higher concentration. Younger halos tend to have lower concentration. Yeah. Sorry, is there a question? Sorry. Oh, okay. Thanks. Great. Sorry, is there a question? Okay.
I would have think that the halo concentration was different just because I was thinking if I have a cluster, I might have more, satellites and therefore satellite, halos. But yeah, if you can talk about that.
Great. So you anticipate my next slide. Thank you. So far I've just been talking about, so I haven't quite introduced the concept of a subhalo yet, but I've just been talking about host halos that are distinct halos unto themselves that are not found inside any other dark matter halo. But there are also subhalos, which are themselves halos unto themselves, but happen to fall inside say the virial radius of a larger dark matter halo. And it is absolutely true that more massive halos have more and more subhalos that are inside them. This is a key fact about CDM structure formation that we're going to leverage to be able to make predictions for galaxy clustering. So you're anticipating a really central part of, really central feature of CDM structure formation that is critical for galaxy clustering. So let's see. Running a little short on time, so I'd like to skip. Okay, so right, so dark matter halos have subhalos that are inside them. Dark matter halos also evolve through the successive mergers of smaller and smaller halos, which merge together and form larger halos, and those merge together and form larger halos still. The sort of industry standard technique for being able to make predictions for this halo evolution is the halo merger tree, which quantifies exactly this phenomenon that I just described of smaller halos building up, merging together and building up more and more massive halos over time. And so the kind of mental model of how halo growth proceeds, sort of tying together many of these different pieces. So at very early times, all dark matter halos in CDM experience this fast accretion regime when they're very rapidly assembling their mass. Mergers are very, very common, and concentrations are very low. Concentrations in sort of at early times are typically around 3 or 4. All halos eventually transition to a slow accretion regime, which really just means that mergers with other halos become much more rare. Their mass accretion rates drop. And mass now piles up onto the outskirts of a halo. Whereas, so this is essentially because the dark matter halo concentration is defined by the ratio of the boundary of a halo to the sort of internal scale radius. Then concentration increases over time as mass piles up on from the outside. So this is really the basic mental model I think I have of how CDM structure growth proceeds at the halo level. Okay, so that is most of what I wanted to cover with sort of basic background of Lambda-CDM structure growth. And really what I'd like to spend most of these lectures focusing on is models of the galaxy halo connection. So how we can go from what we can simulate, which is a distribution of dark matter halos with internal structure and clustering properties. This is what we can directly simulate, to things that we can actually observe, like the two-point clustering of galaxies and their lensing. And so what I'd like to give you a picture of is really just the sort of landscape of models of the galaxy halo connection for different ways that we can do this, which capture different levels of complexity, have different computational demands. So this is a schematic taken from, I forgot to include the link here, it's on a different slide, from a review article in 2018 by Risa Wexler and Jeremy Tinker. I think they have this really nice way of organizing the landscape of models of the galaxy halo connection. Of here on the, let's see, for you it's the same. Yeah, so for you on the left, the most computationally demanding models are direct hydrodynamical simulations, in which sort of baryonic feedback is included with subgroup prescriptions. These are the most computationally demanding, but these are also the most predictive of all models of the galaxy halo connection. Proceeding the next step to the right are semi-analytic models of galaxy formation, which rely on gravity-only in-body simulations, but use full merger tree information for their predictions. A next step, simpler, are sort of a relatively new class of models called, so let's see, Risa and Jeremy called it empirical form modeling. I think maybe my slides, I call it semi-empirical modeling. This is a class of models that also makes predictions that are complex like semi-analytic models, but are much cheaper. And let's see, proceeding to subhalo abundance matching. This is the class of models that I'll talk about in the next lecture. These do not rely directly on merger tree information, but they do use sort of subhalos in their sort of predictive technique for galaxy clustering. And then finally, tomorrow, I'll talk about halo occupation models, which completely ignore subhalos, but instead just synthetically sprinkle galaxies inside the virial radius of a host halo. So in a nutshell, this is the landscape of models of the galaxy halo connection. And just to summarize, so let's see. Some of our best evidence today for one of the sort of very exciting recent results about dark energy, that it may have an evolving equation of state or maybe a signature of modified gravity, come from pure geometry probes of Lambda-CDM. And really what I'm focused on in this set of lectures is structure growth probes and how it is that we can make predictions for how structure evolves in the nonlinear regime using simulations. And really, I think the main takeaway is just that we cannot directly predict, sort of with fundamental theoretical tools, the things that we can actually observe. And instead, some additional models, in this case, models of the galaxy halo connection, are sort of mission critical in order to be able to make predictions that are comparable to what we can actually observe with our survey telescopes. So, okay, I think I'll just conclude now.
Thank you, Andrew. So I think we have time for one question before the short break. Any questions?
Hi, thanks for the talk. So I was wondering if there could be any or analytic predictions for like subhalo, like a subhalo mass function, or like at a given mass, how many subhalos would we expect to find within a given host halo?
Yes, there are. So I give a link. So basically, the kind of one-stop answer for predictions at the 10 to 20% level for everything that I've talked about comes from extended pressure trajectory theory. That includes halo mass function, halo bias, and also substructure abundance and more. So I have a link to a review article. This is written by my advisor in 2007, Andrew Zentner, there, that I think gives us I think a lengthy chapter on how to predict the abundance of in particular of subhalos, of substructure and dark matter halos using EPS theory. And again, the sort of refrain is that yes, you can make predictions with sort of core analytic techniques, and they're only accurate to the 10 or 20% level. And so we rely on simulations to even calibrate sort of free parameters of these theoretical techniques. But yes, you do get lots of insight into what you should generally be expecting from EPS.
Thank you.
Just a quick question. So you showed like R, like delta, that's the realization radius, correct? This one.
Yeah.
This is the realization. Okay. Just
right. Yeah. So you must pick a particular smoothing scale in order to be able to define how the sort of the collapse region from the density field. Yes. Is that what you're?
yeah.
That's
Yes. Just making sure.
Yes. Yeah. Sure. Thanks.
Okay, so maybe we can continue a question on Slack for now and go for a short break.